So what I'm looking at is one of the protocols um, for MPC in the head. So that's multi-party computation, MPC. And in the head is you're running the protocol virtually in order to generate a ZK proof. So that's the basic idea. This is related to secret sharing, so locally identifiable secret sharing, or they can relax the local identifiable constraint. So this has to do the locally means you're picking some subset out of a collection of players or parties that you're sharing the secret amongst. Essentially, they are able to correlate this to some linear algebra operations. And what I'm doing is picking apart the linear algebra operations and how they relate to message passing. So still have a ways to go before I can present a coherent interpretation. There are summaries of this given by the author at the BIU schools, but I want to get into the details so that I can sort of walk us through how we would do implementations of these kinds of things. So that's essentially, the research that I'm doing right now. What I've got on the page is the actual solution and learning how to just even understand the notation. So I can walk you through what's going on there, and then sort of say what the steps are in the future. So there are two pieces of the protocol. So you're gonna share out some secrets, and then so they're starting with some protocol that does something, and they're going to generate a ZK protocol. So they already have some secret sharing capability that's given by some multi-party protocol, and they're gonna generate a new protocol from which they can provide a ZK proof. So that's an important part of the setup. So the notation here is saying that, starting with the original secret sharing, so you have some secret that's coming out of some space of secrets. So for us, you could think of that as like generating a fresh name. And then you're going to break it up into n shares. So each of these are pieces of the secret. And then there's a function which allows you to reassemble them back to get the original secret. So if you, and typically you'll look at a variety of these, like, so you have to have some number of the shares before you can successfully generate the secret or reassemble the secret. This means they're going to pick U, I, and VI using a uniform distribution from some field where you're taking out the zero object. So the field, could be the reals or the complexes, whatever it is. Typically, I think they're talking about finite fields because they take the size of it. So So you have some finite field. You randomly pick using a random a random choice with uniform distribution. You randomly pick ui and vi, and that's for all the I in bracket in. So then they're going to define a block of the matrix, of some matrix. So C0 is taken from the invertible matrices whose entries are taken from the field F. And the ijth entry is going to be ui to the j plus 1 vj to the I plus 1 plus ui vj plus 1 if I and j are not the same. And if they are the same, then you pick ti out of the shares. Does that make sense?
Yes.
Okay, all right. So now you're going to define C is going to be given by a block in the upper left quadrant. That's C0. All right, so this is going to be n by n, and then this is going to be the identity n by n, the identity n by n, and the 0 n by n. Then you generate, you randomly pick some matrix, where your random choice has a uniform distribution from the invertible matrices over F with 2n. And you define, I'm sorry, this is just the matrices, not the invertible ones. This is the invertible ones. And then you define A to be C composed with B inverse. And now you're going to pick the ith row and call it ATI, and the jth column of B as BJ. And this is the share that you're going to send out. So the ith share of S is going to be this thing.
So this means that we are somehow encoding our data in some in this matrix.
That's correct.
Yeah. And we are picking something from the matrix, which not to me, but something that it's not, that cannot be correlated to encoded data, right?
Yeah, well, it has some correlation, but the correlation has specific properties. Basically, the property that this is going to guarantee is that if anyone tampers with their share, right? So they received a particular share, and then in the protocol they send back a tampered version of it. So they swap out some bits, let's say. Then that party is called a cheater, and all the honest players will all agree on who has tampered with their share. That's the protocol. yeah, there are various versions of it that are at play here. So they start with a local version of this and then expand it to the entire thing. And what I'm working on is picking apart how the matrix operations correspond to the message passing in the MPC. So this is not at all obvious. So that's what I'm doing, and I want to do it in such a way that I can then map this into a row setting, right? Which would be quite pleasant, right? If there's some subset of row for which we can, identify some nice linear algebra operators, that would be, at least with respect to ZK stuff, that would be quite lovely. So that's essentially what I'm doing. But as you can see, there's a lot of stuff to slog through in order to pick this apart. But that's essentially what I'm up to right now. And this is just one of many protocols that are doing this, and it's this is largely focused on. I mean, at the end of the day, the protocol is only, well, I don't want to say that just yet because I'm not 100% sure, but there are some constraints on this protocol that we probably want to relax. So that's kind of what I'm doing is picking apart this protocol and figuring out the how it relates to the actual message passing. And by that what I mean is that the linear algebra operations correspond to some message passing. Okay, so now
can I ask you how to decide, for example, the size of this field and and the distribution of when we pick this I and J? How can we be sure that this gives us the level of security that we expect?
Yeah. So this has to do, the level of security is directly correlated to the size of the field. So their theorem, so delta is some parameter, and for which, if the thing is for all delta greater than 0, you get the secret sharing property. And then they show that as long as delta is greater than n, where n is the number of shares you divide the secret up into. So it's n squared times n plus 1 over the size of the field minus 1. Then you get the secret sharing property.
And they're providing some kind of proof for that, right?
That's exactly that's correct. That's exactly right. Yeah. So these are interesting parameters to the protocol, to be honest. I'm a lot of this has to do with, you're hiding information inside the field, you're hiding information. It's like different ways to the cup and ball game, right? So some of the places that you're hiding is in your choice of field, and some of the places that you're hiding is in the way you've shared up the secret. Yeah, so it's like you've got two knobs on the way you're doing your information hiding.
Yeah, I can. It's difficulty to grasp, how to work with this stuff. I don't have enough knowledge.
It's an interesting space. I'm used to language theoretic stuff and category theoretic and type theoretic stuff, and process algebraic stuff. So this is a little different flavor of computation or reasoning about computation. So they tend to use what I would consider to be naive classical mathematics to prove properties about their protocols. So it's an interesting approach. Okay, let me switch over real quick. And can you see this?
Yes.
Okay. So what Mike and I are working on now that we've got the system more or less nailed down, is looking at key examples. So of course, one of the key examples is prime. Prime is a very interesting a formula, right? So it says it's not the identity, and it's not the composition of things which are not the identity. That's the prime formula. Now, model theoretically, as opposed to proof theoretically, you can just calculate directly, right? So the meaning of this is going to be the meaning of top take away 0 intersect with that. Sorry, top take away 0 intersect with that. And we can calculate what this is. So this is going to be, so the negation is going to be top take away this part, right? So this part is all the ones which are parallel composition or compositions, which are not empty. I'm sorry, not the 0. Right, and then you pull that out of top. So it's taking the intersection of top minus 0 is just going to be the non-zero versions of these things, and that's easily seen to be the combinators. Proof theoretically, you want to do something different. Right? So proof theoretically, what you want to do is you want to take, well, that should be top. Anyway, this shouldn't be pi, it should be top. But you want to take K, the logical formula, or the type. These should be underscored. We're still sort of debugging these things, the notation. But you want to take the type K of at top, right? So you can put anything here, and then each of the different combinators. So again, we're proving prime for the row combinators. That means for each of these things, we get a corresponding type constructor, which is the underscored thing. And if you recall our formulae, we have top 1 empty, which is the same as false, negation, or, and then we have De Morgan, right? So we can get and as well as or. And then the other stuff that comes from them, the core of the construction. All right, so here, so we're going to form a big disjunction over each of the combinators, and we're going to say that implies prime. And likewise, you want to show that prime implies that. And when you have that, then you've got the logical equivalence of these two things, which means that the sets are going to be the same. Does that make sense?
I'm not sure what when you say these combinators implies prime.
So what we're saying is we're going to start a we're going to make a formula. These are not the combinators; these are types picking out. So this type here is going to be the type of all processes that look like K of some name. And then this union is going to be or the set of all processes that look like, for each of the different combinators, blah, 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 up to, so if we're running through, the reason I put K first is because it's the only unary operator. So if we did it in terms of unary to binary, we'd go K, message, branch left, branch right. And then we do D and S, right? So you do K of top, at top, K of at top, or message of at top, or branch right of at top, branch left, or branch left of at top, or you see what I'm doing?
So you're not saying just the constructors. You much more.
Yeah. So it's at top. So since it's at top, that means it's it's all the processes that are K's over all the names, or all the processes that are messages, over all the names, and so on and so forth. So this is a big formula. I mean, the formula is not very big. It's just, but the set is potentially quite large. Okay. So that, that set, which is what we calculate here, model theoretically, right, corresponds to this formula. And what we say is that formula implies prime, and prime implies that formula. To prove in the proof theoretic way what we calculate model theoretically, this is what we do using these inference rules. Right. So that's the difference between the two approaches. So you start with these inference rules, and then you want to prove something that corresponds to this model theoretic statement here. Right. So that's the way the two approaches differ. So sometimes this kind of calculation is going to be easy and direct, and sometimes running these inference rules is going to be easy and direct. Right. So that's why, so you want to be able to avail yourself of both, model checking and proof generation. The other advantage of this is that this gives us a form of prologue. No, it's not prologue the way you might have become familiar with it programming in some logic and computation class. But you can do the same kind of proof search. So you can generate a prologue-like language where your programming language doesn't come from, it comes from your formulae. So it comes from the things on the right-hand side of these of these type judgments, or another way of putting it is, this is your programming language. This is the syntax. These two things are the syntax of your programming language. And and then you write prologue style inference rules, and then you do proof search to verify that you can get to a proof from your inputs to your to the body of, or from the body of the implication to the the antecedent, right? You go backwards. So so this is also nice. It gives us a, you can get a logic programming language from your original programming language, right? So you start with some programming language that has at least this structure here, and then you can generate a logic-based programming language that follows that, follows the the notion of computation that's provided in the original programming language. So you get both a logical view and a rewrite view, right? So those are the another advantage, right? And then of course you also get the search capabilities, right? So the search capabilities come from these type inference rules. They're not inference rules, but the type assignment rules. So with the type assignment rules, you're constructing the witnesses. So that's the, you know, the reason you want to be able to look at computation from all of these different angles. So what we're doing now is constructing the proof. We're struggling with the fact that negation is so powerful. So, you know, we want to be careful to contain or confine how the negation works with the proof rules. So that's where a lot of the work is in refining the system that we presented here, so that, you know, you get interesting statements like prime, but negation doesn't, you know, sort of knock you out of the ballpark. But it is worthwhile noting that prime gets its power from the negation. So that's something that I wasn't aware of. I hadn't really realized that that this correspondence between primality and single-threadedness, sort of the sort of expressiveness of that, the expressive power that allows us to see that correspondence, is all coming from the negation.
This is interesting.
Yeah, that was new to me. I hadn't seen that before. So, yeah, and it's because you've got this kind of double negation going on over here. That is what's really doing the trick. You know, this isn't interesting. It's this double negation here. You know, not of the knots, the composition of the knots. That's what's creating this, our ability to see that primality is corresponding to single-threadedness. Anyway, so that's kind of where the research side of of our chain is right now. I wish I could give you more exciting and sexy results, but a lot of research is, you know, a lot of calculation and tough slogging.
Oh yeah, but it's always, you know, something new. So
yeah.
So can we say that this somehow formalize this notion of type-driven development? If we are starting with a language which doesn't have any kind of these nice properties, and when we generate types, we can like start programming in this type-driven development, because we will specify some types. We will search available programs, and in that sense, we are like making these holes that we will that type checker will give us. What can be put in these holes.
Yeah, I mean, I definitely, I mean, it's, one of my goals is to create systems that facilitate and foster type-driven development. I mean, what people should be doing, in my opinion, is working both sides of the problem, right? So you have your original notion of computation, which is given here. Um, at least minimally, this pins down what kind of computation has to be. It may have all kinds of bells and whistles, but at least it has this much structure. And then, so you can write down intuitively, it's this. You started here, so you probably have some programming intuitions as to how to solve your problem. But by the same token, you want to reason at a higher level. So you write down some formulae here, which are sort of specs for what you intend your computation to be. So you're working kind of both ends, sort of down in the trenches and up in the sky, with the logics, and then you use these proof rules to sort of have heaven and earth meet. That's that's the idea. So you show that your program really is a witness for your spec. So,
yeah, this makes sense. Not like you're building your language in the you have like version 10, and then you figure out that your types and type system is not like a good fit for.
Yeah. No, yeah. For sure. What this does is it makes sure that you absolutely have a good fit for your programming language. The types in the programming language are a perfect fit. Yeah. And this allows you to say more things about your programming language than what type systems usually do, right? So this sort of shifts you from specifying what happens at the ports of your chip, at the pins of your chip, to specifying, for an entire slot in the board, what the behavior of the thing that goes in that slot should be, not just what's happening at the pins.
Yeah.
So that's the shift in thinking. All right, that's what I've got for today. I appreciate the chance to engage, and hopefully with luck, I will have a little more forward progress. Thanks to all, and I will see many of you in Dev Stand-Up in about 20 minutes or so.
Thanks.
Thank you.
And good luck.
Cheers.